All right, students, now that you've gone through the procedures of how to do this experiment, we're about to go through a practice set of calculations. Again, this is experiment 12, vapor pressure of water. Let's always keep in mind what our objectives are, right? We are going to determine the vapor pressure of water as a function of temperature. Then we're going to use the vapor pressure data to construct a Clausius-Clapeyron plot. In other words, natural logarithm of the vapor pressure against the reciprocal temperature. And we're going to use the slope of that plot to determine the enthalpy of vaporization of water. You all remember our setup for the experiment. It's a suspended graduate cylinder that has a bubble of air inside of it. And as the water is heated, the temperature increase causes the bubble to expand, both because the air inside expands and because water vapor begins to accumulate in there. Don't forget that before we take any readings, you were supposed to slide the cylinder up and therefore equalize the level of water inside and outside, because when they are at the same level, we can say that the pressure on the inside is the same as the pressure on the outside, which is the one that we can measure using a barometer. Here is a sample data set that I borrowed from some former students of mine. This is the old data set, the old data table that we used to have. You are now receiving a different one. So this was from Reed and Ben, very good friends. Reed was a very, very smart guy, and I don't know, many of my former students, they chose more like physics and engineering instead of chemistry. But Reed and Ben were very, very good friends, and Ben, actually, I never saw him again. I heard that he had gotten some kind of skin disease or something. And then Reed was very funny because he used to like to play all these tricks. He was very flexible, kind of like contortionist. He used to like bend his fingers and stuff, and everybody went like, "Ew, how can you do that?" Anyway, so I'm gonna take this data set that you see here, they collected, and this would be what it will look like when it's transferred to the new data sheet that we're going to be using in this revised version of the experiment. All right. Now, as the data sheet indicates, we are supposed to set up an Excel spreadsheet. All right. And we're going to put in the columns that are in there. So I've gone ahead and set up an Excel spreadsheet here. You can see the columns there on the top, and then you can see the values that I've already inserted, the volumes of the bubble at the different temperatures. Now, one of the first things we had to do is we're going to be using the ideal gas law. So one of the first steps we have to carry out here is to convert Celsius to Kelvin. You have several options. One thing you can do is you can simply do your calculations by hand and then simply input the numbers in here. And you can do the same thing for the rest of the Excel spreadsheet here. However, I'd like to give you a chance to look at, if you want to use the formulas in Excel, how you can do that. So let's go look at that. We're going to be working here with the Excel spreadsheet that you're supposed to set up for experiment 12, vapor pressure of water. I have already put in the different columns that we were asked to put in there. And as well, I've already gone ahead and input the data that was given in the sample set, both the volumes of the bubbles at the different temperatures in degrees Celsius. A couple of things that you can do. For example, let's say you want to format this so it looks nicer. You'll notice that right now the little O in the degrees Celsius is not a superscript. So one thing you can do is once you select the cell, you can go up here to where the formula bar is and select that little O there. And now you have several options, but typically in this font area, if you expand it by clicking this button here on the bottom right, it'll open up a set of menus that will allow you to work on it. You probably can't see them here on the video, but there's one for to put in a superscript, and that's what I just did. I clicked it and clicked OK, and now you can see how it comes up as a superscript. Sorry that the video will not show you that. The next thing we want to do is we want to convert the temperatures in Celsius to Kelvin so that we can use the ideal gas constant in calculations and the ideal gas law. Again, you can do these by hand and just input the values, or you can let Excel do it for you. To let Excel do it for you, you write the formula in by clicking in the cell, type in the equal sign. That activates the formulas and functions capabilities of Excel. And now select the cell you're going to be converting. In this case would be cell B2. I'm just going to click on top of it. And as you can see, there's like a moving little square around it. And the cell destination, the cell location, actually B2, is now written over here. Now I'm going to add plus 273.15, which is the formula for converting into Kelvin. Now I'm going to click the Enter key, and there's my value there. I have other values to put in, but rather than copy or rather than write the formula all over again, what I can do is I can come back here and select that cell. Notice there's a little frame around it, but in the bottom right, there's a little kind of like square. As I hover my cursor over it, the thick white plus sign becomes a thinner black one. And if I click and hold there and then drag my cursor down, what will happen is Excel is going to fill in all these cells with the same formula, and it will adjust for the different values that I'm doing here, 70, 65, 60. Now, the next step we have is we have to adjust significant figures. As you can see, our Celsius temperatures have 1 decimal, but Excel automatically put in 2 decimals in here. So in order to fix that, what I can do is, again, I can select and then drag all the way down to select the whole column. And then up here in the menus, there's one that says number, and there is one item here that allows you to change, to increase or decrease the decimals. In my case, what I want to do is I want to decrease the decimals. So I'm going to click that one, and what will happen is now everything is to 1 decimal place, properly rounded. All right, so those are some of the tricks that you can do with Excel. Thank you. Okay, this is what the Excel spreadsheet looks like after we have converted the values of Celsius into Kelvin and adjusted for significant figures. Now our next step is we need to make a correction to the volume of the bubble. And let me explain why that is. This is what the graduate cylinder looks like with the inverted format here. And the way we're reading the meniscus, right, is right at where the meniscus is at the lowest, right? That is where we take the measurement. Now remember, the graduate cylinder is inverted. In a properly used graduate cylinder, this instrument is calibrated already to account for the fact that in reading at the meniscus, there's a little bit of water on the sides that we're not taking into account, but the calibration of the instruments compensates for that. The problem now is that we have it inverted, and so there are these kind of upswings of water here on the sides. Actually, if you were to project this around the circumference of the graduate cylinder, you would be looking like kind of like a sort of like a little like a donut or like a little ring or something like that. So that is essentially causing us to overestimate the volume of the bubble. So we're going to have to introduce a correction here. And what we'll do is to correct for the overestimate of the bubble volume, we're going to subtract 0.2 milliliters from each volume. Okay, so I'm going to take us back here to the Excel spreadsheet. And what I've done is I have already entered that corrected value in there. So each one of these in column D are whatever was in column A minus 0.2. Okay, our next step is to find out what is the vapor pressure of water, but for reasons you'll understand is we have to first calculate what is the partial pressure of the dry air inside the bubble. And for that, we're going to use the values down here that we took at the lowest temperature. That was the temperature, remember, that we proposed at which there is no water vapor. So all we have in there is quote-unquote dry air. So let's take ourselves to that point, which for Reed and Ben's data was 3 degrees Celsius. Yours might be closer to 0, might be a little higher, close to 5, doesn't matter. This is our lowest temperature point. What we're saying is that at 0 degrees Celsius, there should be no water vapor. The bubble is just dry air. What we want to find out is, well, how many moles of dry air do we have in here? And for that, we're going to use the ideal gas equation. N equals PV over RT. So in the case of Reed and Ben's data, we had a pressure of 760.0 torr. Remember that because we equalized the meniscus inside the grad cylinder with the water level on the beaker, the pressure inside should be equal to the pressure on the outside. Volume of that bubble corrected was 4.4 milliliters, and the temperature wasn't quite 0. It was 3 degrees, which is 276.2 Kelvin. Now, normally in the past, what we've done is we have converted the pressures to atmospheres and the volumes to liters. But this time what I'm going to do is I'm going to take the R constant, 0.08206, and convert liters atmospheres into milliliters torr. And that is the value you end up having for the gas constant using these units. It's the same value. Don't worry about it. It's just different units. So let's go ahead and plug all our numbers here and find out how many moles of air are in this bubble. PV over RT. Let's put all these values in there. Be careful to make sure you have the correct units and also the correct values where they belong on the fraction here. And now let's check for the units. So torr will cancel out with torr, milliliters with milliliters, Kelvin with Kelvin, and the units of moles will flip up, so that will give us a value here. Now, when we look at the measurements here, we see that our volume, 4.4 milliliters, only has 2 sig figs. That means we had to round our final result to 2 sig figs, and that's 1.9 times 10 to the minus 4 moles. Let me make a comment here about the volume measurement. When Reed and Ben did this experiment, we used to have smaller beakers. And so the regular long graduate cylinders would not fit in there. We had to use some shorter ones. But we had to sacrifice some precision and we could only read them to 1 decimal place. That's why these volumes here have just 1 decimal on them. You may have a data set when you receive yours that has the 2 decimal places. So if that's the case, then please adjust your sig figs for that, all right? Okay, now let's say that we are reading the bubble at a higher temperature, all right? At a higher temperature, now the bubble has both air and water vapor in it. To find the vapor pressure, we're going to apply Dalton's law that says that the total pressure in the mixture will be the sum of the partial pressures, in this case, air and water vapor. Because we equalized the pressure between the inside and the outside, that means that the total pressure inside equals the pressure on the outside, which is whatever the barometer said that it was. Therefore, we can solve for the water vapor pressure by taking the outside pressure and subtracting the partial pressure of air. Oh, wait a minute. How do we find that out? How do we obtain the partial pressure of air at all these temperatures? Well, remember, at the lowest possible temperature, we calculated a certain number of moles of air. We said that it was 1.9 times 10 to the negative 4 using Reed's and Ben's data. Now, your data might have a different value there, but we know that there is a constant number of moles of air. We are assuming that as the temperature increases, all that air stays in there. None of it escapes out into the atmosphere or something like that. So that means that at each temperature, we can calculate what is the partial pressure of these moles of dry air. So for example, let's say we take the highest temperature value, which was 347.2 Kelvin, and we saw that at that temperature, the bubble had a corrected volume of 6.7 milliliters. Again, remember in this set, we are only good to 1 decimal place. It may be that in your data set, you'll be able to have 2 decimal places. So what we're going to do is we're going to use, again, the ideal gas equation to solve for the pressure of the air. That'll be nRT over V. And remember, the number of moles of air is the same all throughout the experiment. That doesn't change. Once we have calculated how much it is, it stays the same for the whole experiment. What is going to change is going to be the temperature and the volume. So let's plug in these numbers that we put in here. Okay, so we have moles of air, 1.9 times 10 to the negative 4 moles. Then we have the value of R. We're using this modified value, 6.237 times 10 to the 4th in units of milliliters torr. And we said the temperature here was 347.2 Kelvin. The volume, 6.7 milliliters. Let's go ahead and make sure that these units cancel out. The moles cancel out. The milliliters cancel out. The Kelvin cancel out. Sorry, these lines came off a little offset, but you get the idea, right? Once more, we are limited to the 2 sig figs of our volume measurement. And so once we have done all these calculations, we get 610 torr. So what you're going to do is you're going to repeat this calculation for every data point. Remember, the only thing that's going to change is the temperature and the volume. R stays the same, and the number of moles of air stays the same. Now, if you want to use the formulas in Excel, I'm going to show you how you can do that. In this second set of operations with Excel, we're going to tackle a couple of things. First of all, we're going to say, what is the corrected volume here? If you don't want to do it by hand, you can simply again enter the equal sign, which activates the formula functions of Excel. And we're trying to correct each one of these volumes by subtracting 0.2. So I'm going to select the first cell, A2, and it's going to show up here in D2, and I'm going to put minus 0.2, and I'm going to click the enter button, and that will give me the value that I'm looking for. Because these are repetitive, I'm going to select that cell again, hover my mouse over the bottom right corner until it turns into a thin plus sign, and then I'm going to click down, hold it, and drag it down so I can get all the values in here. Now, you have already gone through the calculation of the number of moles of air. Remember that the number of moles of dry air does not change. We use the low temperature calculation here to find out how much air was in there. Those same numbers of moles of air, which we calculated to be 1.9 times 10 to the negative 4, are going to be here throughout the whole process at any temperature. So what we'd like to find out is what is the pressure of just those moles of air in here. So what we're going to use is we're going to use the ideal gas equation. So we're going to say that the pressure is going to be nRT over V, right? So we're going to put the equal sign again here. We're going to start out by writing out the number of moles n. In Excel, the way you write scientific notation is by putting a capital E that indicates the exponent, and this is going to be times 10 to the minus 4. To multiply, you had to use the asterisk, and the next value we're going to put in is the value of R. And we're using the new value in milliliters torr, so 6.237, again, E to the 4th, close the parenthesis, and R. Now we need the temperature. We're going to put, again, an asterisk there, and we're going to select the cell where the temperature is, which is here, cell C2. There it is. And now we're going to divide all of that by the volume. Don't forget, we are using the corrected volume here, which would be 6.7. Now that we have all the functions in place, if we have not made any mistakes, if we click enter, it should give us a result. And there it is. Now, before we do any other calculations, let's go ahead and select that. Go ahead and put in the cursor over the bottom right until it turns into a thin plus sign. Click and hold and drag it down but we're only gonna go up till the 50-degree or so temperature. The reason is we already assumed that at the very low temperature, all of the air is the only thing in there. In other words, all the pressure is generated by the air, and we had established that the total air pressure, barometric pressure, the total pressure there was going to be 760. So that's what we're going to write in there. In other words, you don't make a calculation for this item here. Now we had to fix sig figs because our volumes here are calculated to two sig figs only. So once more, we're going to select here this whole column of values here. And we're going to eliminate all those decimals by using the symbol here, decrease decimal. So we'll click it a few times and it'll give us the values with no decimals. Now technically, we have to round these numbers to two sig figs. Right now, they have actually 3 sig figs. If you decide to leave it the way it is, I'm not going to argue with it. But if we're going to be true to our rules here, we would have to round these. So what we're going to do is we are going to change these manually, if you don't mind, and we're going to change this. What I can do is I can come in here and click over the F here, and then right click. I'm going to insert a new column in here. You might not have seen that. And what I'm going to do in here is I'm going to put in here the adjusted pressure of the air. All right. And what I'm going to do here is I am going to take these numbers here on column E and round them to two sig figs. So this will be 610. This will be 640, 670, 680. This one will stay at 680, 690, and of course this one stays at 760. So that is the way you can do this with Excel. Again, if you decide to leave the numbers that we have on this column here directly from the calculation, I am not going to argue with that. It should be okay. I'm just trying to be kind of like super legit here about sig figs. Okay, so those are the values that we would get. When you go back to the PowerPoint, those are the numbers that I'm going to be putting down in the PowerPoint. Thank you. Okay, we're back here to our table, and as we explained, we have used a corrected version of the values of the pressure of the air to account for the fact that we can only have two sig figs in here. Be mindful again about this value here. Remember, we said that at the lowest temperature, all of the pressure is due to the dry air only. So whatever the pressure is inside the bubble equals the pressure outside, which is 760. But all of that is due to air. So the air pressure at the lowest temperature, we don't calculate it. It simply is what it is. Now what we're going to do is we're going to calculate what will be the vapor pressure of water at each one of these temperatures. Remember, that would be the total pressure minus the pressure of the air. And these are the numbers we get. How do we get them? Well, for each one of these, we took 760 and we subtracted the corresponding pressure of the air at that temperature. When we get to this point is where many times students experience an interesting error, and that is that they get a negative value of the vapor pressure of water, which is not possible, right? And sometimes they think, oh, I must have made a mistake on my calculations. It typically is not a math issue. It's usually an error in the execution of the experiment having to do with things like, for example, not stirring the water enough to get good distribution of temperature, or for example, forgetting to properly equalize the pressure inside the bubble with the outside, and things like that. All right. If your data shows any negative values here, those values are not going to be able to be used for the Clausius-Clapeyron equation. So you'll have to provide an explanation for such an error. Okay, so now we're going to calculate the next set of values, which is the reciprocal of the temperature and the natural logarithm of the pressure of water, so we can do our Clausius-Clapeyron plot. Again, you're welcome to simply do these calculations by hand and then put the values in, but if you'd like to use the formulas in Excel, I'm going to show you how you can do that. Okay, at this point we have entered the vapor pressures of water in this column by subtracting essentially 760 minus the adjusted pressure of the air that we rounded to 2 sig figs. Notice that the formula itself tells you that at the very low temperature, the vapor pressure of water is 0. We have proposed that there is no water vapor at that temperature. In order to get the Clausius-Clapeyron plot, we have to get the reciprocal of the temperature and also the natural logarithm of the water. Again, you can do this in your calculator and just put the values into the Excel spreadsheet, or you can let Excel calculate it for you. Let's go here to this cell here, and let's say we're going to do the reciprocal. This will be equals. This will be, I'm going to go 1 over. I'm going to pick the temperature. Don't forget, you have to pick the temperature in Kelvin, not in Celsius. And that should give me that result. When I click the Enter key, I get this number in there. Once more, I am going to continue doing this. And I am not going to bother with the last one because we're not going to plot the last value here. Remember, that is the value that we use simply to calculate the number of moles of air. So we don't really need the reciprocal of the temperature for the 3 degrees Celsius. If you want to be a little more exact about things, you'll realize that since your Kelvin temperatures had 4 sig figs, these numbers should also have 4 sig figs. Right now they have 5, so what I'm going to do is I'm going to decrease 1 decimal in here to put them back to where they have 4 sig figs only. The last calculation we'll do is a calculation of the natural logarithm of water. In Excel, again, equal sign opens up the functions, and the function for this is ln, and then you put a parenthesis and then pick the cell you want. Remember, we're doing the pressure of water, not of air, so this would be, in this case, cell number G2. Close the parenthesis and click enter, and there's your value. Realize that if you had obtained a negative value for the pressure of water, the function of the logarithm will give you an error. Let's go ahead and do the rest of these. And there they are. By the way, like I said, if you had tried to do the low temperature point, what will happen is if I try to do a log of that, I'm going to get an error message there because there is no such thing as the natural logarithm of 0. All right, I'm going to delete that. And the next thing I'm going to do is I'm going to adjust the sig figs in here. Now, when you calculate a natural logarithm or a logarithm, the first digit in here has to do with the powers of 10 or the powers of e in the case of a natural logarithm. And so we don't count it as a sig fig. All we count is the decimal places. Since our vapor pressures here were supposed to have about 2 sig figs, what I'm going to do here is I am going to take these guys down to 2 decimal places. And there we go. And those are the numbers that I'm going to use in doing my graph. Remember, to do your graph, you've done this already. You're going to be selecting the columns that have the 1 over temperature. That'll be your x. And your logarithm of p. That's going to be your y. And from there on out, you know what to do. All right. Thank you very much. Okay, after doing all of our formulas and adjusting for significant figures, here are the values that we have. And those last 2 columns are the ones you're going to use to do your Clausius-Clapeyron plot. At this point in our semester, you should be able to do this without any extra help. So what you're going to get, if you were to use the data that I had from Reed and Ben's experiment, is a plot that looks like this. Again, don't forget in your graph to put a proper title that indicates what this is about. Make sure you label the axis with the proper units. Just be mindful that logarithm functions don't have units. So the log of p on the y-axis should not have any units. The important thing that we're looking for here is the slope of the graph. So make sure that you've inserted there the the line equation for the trend line. And that is the number we're going to use to calculate the enthalpy of vaporization. So keep that in mind, minus 3410.7. The units of it are Kelvin, and I'm going to let you figure out why the units of the slope are Kelvin, all right? But they are. So remember, the Clausius-Clapeyron equation relates the natural log of the vapor pressure to the reciprocal of the temperature. This has the format of a straight line for which the slope is minus delta HVAP over R. We are interested in calculating delta HVAP, right? So that would be, therefore, if we rearrange that equation, minus the slope times the value of R. Don't forget, the slope is minus 3410.7 Kelvin. And in this case, because we're looking directly at units of energy, instead of the pressure volume product, we're going to use the value of R that's in joules. So the slope is minus 3410.7 Kelvin, and R has a value of 8.314 joules per mole per Kelvin. But we typically do enthalpies in kilojoules, so we're going to add there a conversion for kilojoules. Let's make sure the Kelvin units cancel out and the joule units cancel out, leaving us in kilojoules. We plug in the numbers, and at this point, the sig figs are not going to be of major consequence. That slope, if we were to use it as a unit per se, we know that it would have to be adjusted for sig figs. So we're just going to simply write this as 28.4 kilojoules per mole. Notice that the two negatives kind of like offset each other. And as expected, delta HVAP is a positive value because we expect that vaporization of a liquid should be endothermic. It should require an energy input to break up the intermolecular forces that are holding the liquid molecules closer to each other than they are in the gas phase. The last step that we're going to do is calculating the percent error. For this, we're going to take the accepted value for the heat of vaporization of water as 42.6 kilojoules per mole. Don't forget the formula for percent error is the absolute value of the difference between your experimental value and the accepted value divided by the accepted value times 100%. So our data that we got from my former students gave us a heat of vaporization of 28.4 minus 42.6. We take the absolute value of that. We divide by 42.6 times 100%, and that gives us a total error of 33.4%. And you might say, wow, that's pretty high, Dr. D. I used to be very strict about keeping the percenter under 10%. Well, the truth of the matter is that if you think about the design of this experiment, the way that we are doing these calculations, you'll realize that there are several places where you can have errors, and it really takes away some accuracy from the experiment. I have had students get things like 60, 70% error, but at the same time, I remember about maybe 4 years ago, I had a lab group that got it down to within about 1%. I think they got like a 42 point something kilojoules per mole. So it is possible to do this experiment right, but don't be alarmed if you have a high percent error in this experiment, okay? Well, I hope that helps you to understand how the calculations are done, please give yourself time to work on it. You will be receiving your data set via Canvas as an attachment to a message. And once you have that, you'll be able to go ahead and finish up your lab report. Please take note that the second, or I guess the third page of the lab manual where the data sheet is, we're not using that one. I am uploading into Canvas a different data sheet that has all the questions and all the things you had to do. And you'll be doing your calculations, at least showing one set of calculations on a separate piece of paper that you will also have to upload when you submit your assignment. Thank you so much. Hope you have a great time. We'll see you soon.